In question 1, we've got the point A being 1.8 meters vertically above horizontal ground. Now at time t is 0, a small stone is projected vertically upwards with a speed of capital U meters per second from a point A. Now at time t is capital T seconds, the stone hits the ground, and the speed of the stone as it hits the ground is 10 meters per second. In an initial model of the motion of the stone moving from A to hitting the ground, we are assuming that the stone is a particle moving freely under gravity, and the acceleration due to gravity is modeled as having magnitude 10 meters per square second. Notice here we're not going to use the usual 9.8. We need to go with the 10 meters per square second. And using the model, we need to find the value of U. I will start by drawing a diagram to see exactly what's happening. We've got point A here. We are throwing the particle upwards and then it comes down. I'm going to open up the motion to make it easier for me to see exactly what to do here. We've got the acceleration being negative 10 because it is acting opposite the original direction of motion. We've got the initial velocity being U. We know that A is 1.8 meters above ground, and we know that we hit the ground when T is capital T with a speed of 10 meters per second, which means that the velocity is negative 10 because we took the upwards to be the positive. So when we're coming down, the velocity is negative. So I'll be using V squared is U squared plus 2AS. The final velocity is negative 10, so negative 10 squared is equal to capital U squared plus 2 times the negative 10 times the 1.8. This leads to 100 being equal to U squared plus 36, and therefore 64 is equal to U squared. And if I take the square root of 64, we end up at 8 being the value of U. In part B, we need to find the value of capital T, and I'll be using V is U plus AT. So we know that capital T is the time of flight. We've got the initial velocity being 8. We've got the final velocity being negative 10. So we can simply say that the negative 10 is equal to 8 plus the negative 10 times the capital T. So negative 10 is equal to 8 minus 10t, which leads to 10 capital T is 18, and therefore capital T is 1.8. In part C, we are asked to suggest one refinement apart from including air resistance that would make the model more realistic. The first obvious choice is to say that we need to use a more accurate value for G, whereas an alternative would be to take into account the dimensions of the stone. Modeling the stone as a particle means we have completely neglected the dimensions of the stone, so it would have been more realistic if we took into account the actual dimensions of the stone. In reality, the stone will not move freely under gravity and will be subject to air resistance, and we need to explain how this would affect our answer to part A. So going back to the diagram here, as we leave A, we now need to find air resistance, and for us to land on ground after capital T seconds with a speed of 10 meters per second, it means that capital U here should be greater. So what we need to say here is that the actual value of U will be greater than the answer we obtained in part A, since we need a greater initial speed to overcome the air resistance. In question 2, we've got a train traveling along a straight horizontal track from station P to station Q. Now, in a model of the motion of the train, when t is 0, the train starts from rest at P, moves with constant acceleration, reaching a maximum speed of 25 meters per second. It travels at this constant speed before finally moving with constant deceleration, coming to rest at Q. Now, the time spent decelerating is 4 times the time spent accelerating, and the total journey took 700 seconds. And we need to sketch a speed time graph for the motion of the train between stations P and Q. So we start by drawing the speed and the time axis. We've got acceleration, then constant speed, and then deceleration. The maximum speed attained was 25 meters per second, and we've got an acceleration for, say, capital T seconds. And if we follow that the time spent decelerating is 4 times the time spent accelerating, then if this is capital T, then this is 4 capital T, and therefore the time here will be 700 minus 4 capital T. Now the distance between the two stations is 15 kilometers, and we need to use a model to show that the time spent accelerating by the train is 40 seconds. In other words, we need to show that capital T is 40. Now we know that in a speed time graph, the area under the graph is giving me the distance covered. So we know that this distance here is 15 kilometers or 15,000 meters. So I'm going to say that 15,000 is equal to the area of this trapezium, which is base 1, which is 700, plus base 2, which is 700 minus 40 minus t, and all of it divided by 2 times the height, which is 25. So I will start by cancelling out the 25 with the 15,000, give me 600 on the left hand side. I will proceed by simplifying on the right hand side, so we're looking at 1400 minus 5t and all divided by 2. So if we cross multiply, we get 1200 being equal to 1400 minus 5t, and therefore we get that 5t is equal to 200. Let's divide both sides by 5 to get that t is equal to 40. And therefore we conclude that the time spent accelerating by the train is 40 seconds. In part C, we need to find the acceleration in meters per square second of the train, and we know that the acceleration is given by the gradient in a speed time graph. So looking at the graph here, it's gonna be the rise of 25 over the run of 40. So we're looking at the acceleration being equal to 25 over 40, which simplifies to 0.625 meters per square second. In part D, we're asked to find the speed of the train 572 seconds after leaving P. So let's start by going back to our speed time graph here. We have found that T is 40. Now 700 minus 40 is 700 minus 4 times 40, which gives an answer of 540. So 572 is somewhere here. So I'm going to mark this on our speed time graph. This is the 572, and we need to find the velocity corresponding to the time of 572. So I'll put a V here. One way of approaching this is through a straight line approach. So essentially we're looking at a straight line passing through 540,25 and 700,0, and I need to find the value of V when t is 572. So let me write down the 2 points. We've got 540,25. That's the first point. The second point is 700,0. I will start by finding the gradient, which is rise over run. So it's 0 minus 25 over 700 minus 540. This gives an answer of minus 5 over 32. I will now use the fact that the straight line passing through the point x1, y1 having gradient m is given by y minus y1 is mx minus x1. In this case, it's not x and y, it's t and v. I'll be using the point 700, 0 for x1, y1. So we're looking at v minus 0 being equal to minus 5 over 32 times t minus 700. I'll be substituting t with the value of 572. So we've got v minus 0 is equal to minus 5 over 32 times 572 minus 700. This leads to v being equal to 20, and therefore the speed at 572 seconds is 20 meters per second. Now alternatively, I could have used suvat because during the time of deceleration, the train is experiencing constant deceleration. We have already found from part C here that the acceleration was 0.625. Since the time spent decelerating is 4 times the time spent accelerating, we can say that the acceleration in the final leg of the journey was minus 0.625 divided by 4. The negative sign is indicating deceleration. This gives an answer of minus 5 over 32, which of course agrees with the gradient we found just a while ago here. And I'll be using that v is equal to u plus at. So if I briefly go back to the speed time graph, I'm applying suvat on this leg of the journey. The acceleration is minus 5 over 32. The initial velocity is 25. The final velocity is v. It's what we're trying to find here. The time will be 32 seconds because the initial point here is the 540 seconds and 572 seconds is 32 seconds later. So if we use v is u plus at, we will be looking at v being the initial velocity of 25 plus the acceleration of negative 5 over 32 times the time of 32. This gives an answer of 20 meters per second, which of course agrees with the answer we obtained just before. In part E, we need to state one limitation of the model which could affect our answers to parts B and C. And here we simply need to say that the train is unlikely to be accelerating and decelerating constantly. In question 3, we've got a fixed point O lying on a straight line and particle P is moving along this straight line. Now at time t seconds, the distance as meters is given by this expression in terms of t, and we need to find the acceleration of P at each of the times when P is instantaneously at rest. I will start by finding an expression for the velocity, which is given by the derivative of displacement with respect to time. In differentiation, we get the power down and we deduct 1 from the power. So we've got a third times 3t squared minus 5 over 2 times 2t plus 6. Obviously, the 3 with the 3 will cancel out, the 2 with the 2 will cancel out, and therefore we get that v is equal to t squared minus 5t plus 6. Now the acceleration is given by the derivative of velocity with respect to time. So this is giving me 2t minus 5. And I will start by finding the times at which the particle is at rest. So if the particle is at rest, this simply means that the velocity is 0. And therefore we are dealing with t squared minus 5t plus 6 is equal to 0. So I get t minus 2 times t minus 3 is equal to 0. So we have t minus 2 is equal to 0, or t minus 3 is equal to 0, which means that t is 2 or t is 3. Now for each of these times, I will proceed in finding the acceleration. So let's start with t is 2, which means that when t is equal to 2, the acceleration is 2 times 2 minus 5, which is equal to negative 1 meters per square second. And when t is equal to 3, we get that a is 2 times 3 minus 5, which gives an answer of 1 meter per square second. Now in part B, we need to find the total distance traveled by P in the interval 0 to 4. So the first thing to do is sketch the graph of the velocity against the time. We have already established that V is t minus 2 times t minus 3. It's a smiley-shaped parabola. We have found that the two times at which the particle is instantaneously at rest are 2 and 3. So the graph of V against t looks something like this. Now to find the total distance covered, I need to calculate these three areas here. I cannot go with an integral from 0 up to 4 because the area between 2 and 3 will contribute negatively and will give a distorted answer. I will instead split this into 3 regions as shown highlighted here, which I will call A1, A2, and A3. Each of these will be found by integrating the same expression but with different limits. So let's start with A1, which is the integral from 0 up to 2 of t squared minus 5t plus 6 dt, which is equal to t cubed over 3 minus 5t squared over 2 plus 6t, and the limits are 0 and 2. Let's plug in the upper limit, which is giving me 2 to the power of 3 over 3 minus 5 times 2 squared over 2 plus 6 times 2, and the contribution from the lower limit of 0 is simply 0. So this is giving an answer of 14 over 3. Now for A2, I'll be integrating from 2 up to 3, the same expression. So we've got t squared minus 5t plus 6 dt, which is again t cubed over 3 minus 5t squared over 2 plus 6t, with the limits being 2 and 3. If we plug in the upper limit, we get 3 to the power of 3 over 3 minus 5 times 3 squared over 2 plus 6 times 2. And now it's the time to plug in the lower limit of 2. So we're looking at 2 to the power of 3 over 3 minus 5 times 2 squared over 2 plus 6 times 2. If we evaluate this, we get an answer of negative 1 over 6, and we are not surprised that we get the negative answer because this area lies below the horizontal axis. I will then proceed with A3. So A3 will be the integral from 3 to 4. Again, we've got the same expression integrated, which will give you the same result with different limits. So t cubed over 3 minus 5t squared over 2 plus 6t. The limits are 3 and 4. If we plug in the limit of 4, we get 4 to the power of 3 over 3 minus 5 times 4 to the power of 2 over 2 plus 6 times 4. And then I will substitute the lower limit of 3, which is 3 to the power of 3 over 3 minus 5 times 3 squared over 2 plus 6 times 3. Let's plug this on the calculator to get an answer of 5 over 6, and therefore the total distance will be found by adding the three areas up. The negative 1 over 6 will of course become positive 1 over 6. So we're looking at 14 over 3 plus 1 over 6 plus 5 over 6, which gives an answer of 17 over 3 meters for the total distance covered in the first 4 seconds of motion. In question 4, a vertical rope PQ has its end Q attached to the top of a small lift cage. Now the lift cage has a mass of 40 kilograms carrying a block of mass 10 kilograms as shown in the figure here. Now this is raised vertically by moving the end P of the rope vertically upwards with a constant acceleration of 0.2 meters per square second. We are assuming that the rope is light and inextensible, and we are neglecting air resistance, and we need to use this model to find the tension in the rope PQ. Now the first thing to do is obviously add all the forces acting here. We've got the tension in the rope pointing upwards. We've got the weight of the lift itself, it's 40g, and the weight of the block, which is 10g. Now this is accelerating upwards with an acceleration of 0.2 meters per square second. So I'll be considering these all together. So I'll be doing forces acting upwards, which is T, minus forces acting downwards, which is 40g plus 10g, being equal to the combined mass of 50 kilograms times the acceleration of 0.2. So we're looking at T minus 50g being equal to 10, and therefore T is 10 plus 15g, which is 50 times 9.8. And if you plug this on the calculator, you get that T is equal to 500 newtons. Now in part B, we need to find the magnitude of the force exerted on the block by the lift cage. So looking at the diagram once more and concentrating on the block here, the block is feeling its weight and it's also feeling a force through the contact between the block and the lift cage. So I will call this R, and similarly the lift cage is feeling the same force but in the opposite direction. So we've got an R pointing downwards. So the forces I'm writing out in blue here are acting on the block, and the forces that I'm identifying with red are acting on the lift. So considering the block is moving upwards, so forces acting upwards minus forces acting downwards, it's going to be mass times acceleration. This means we're looking at R minus 10g being equal to 10 times 0.2. So we're looking at R being equal to 10 times 0.2 plus 10 times 9.8. This gives an answer of R, which is equal to 100 newtons. Now, alternatively, we could have decided to consider the lift. So considering the lift, we've got forces acting upwards, which is the tension, minus forces acting downwards, which is the 40G, plus the R is equal to mass times acceleration. We have found from part A that the tension is 500. So 500 minus the 40G minus R is equal to 40 times 0.2, which is 8. And therefore get that 500 minus 40 times 9.8 minus 8 is equal to R. If we evaluate the left hand side, we get 100 to be the value of R, which of course agrees with the value we obtained through considering the block.